Hello everyone, I'm Zhong. Today, I will present our recent work, 3D LiDAR mapping in dynamic environment using a 4D implicit neural representation. Building accurate maps is an important task for autonomous driving and mobile robots. Traditional method always fills scans from different time steps into a 3D map representation. However, if the environments contain dynamic objects, they may leave some artifacts in the map, which can be harmful to downstream tasks such as localization and planning. To solve this problem, in this work, we propose a 4D map representation. We first built sparse voxels around the point cloud, collecting from different time steps, and randomly initialize one time-independent feature vector on each corner of each voxel. Once we want to correlate the TSDF value of one coordinate, we first use trilinear interpolation to calculate the feature vector of this coordinate, and then feed it into a global shared MLP. We regard the output as the weights of several basis functions. We summed up all the weighted basis functions to obtain a time-varying signed distance function, which can be correlated at different time steps to get different value. For the basis functions, we set the first function as a constant 1. In this way, we can decompose the time-varying function into a time-independent static part, which is the first element of the MLP's output, and also a time-varying dynamic part. As our map representation is fully differentiable, we can optimize the feature field, the MLP, and the basis functions jointly by gradient descent once we know the difference between the prediction and our expectation. We sample along each ray in each scan to collect the training data. We split the ray into near surface part and free space part, and sample several points in each part. For the near surface area, we first calculate the project distance from the sampled point to the end point, and generate loss only if the prediction value is larger than the project distance or has the wrong symbol. We also add the gradient constraint to meet the natural property of the signed distance function. For the free space area, we simply optimize the prediction to a truncated value. And for some area we think is certain free, we directly add this constraint to the static SDF, which is the first element of the MLP's output. Finally, we sum up all the loss atoms as the full loss function to train our map till converge. Here is the result of our method on the KT dataset. We take the sequential scans as input and optimize a 4D map can be queried at any location and any time steps. Then we can extract the static map from our 4D representation and segment out the dynamic objects based on our static map easily. For the evaluation, we first evaluate our method in surface reconstruction in dynamic environments. The result shows we can build clean and accurate maps. We also evaluate our method on the public benchmark for dynamic object segmentation. The result shows our method has much better associated accuracy compared with other state-of-the-art baselines in autonomous driving scenes. In summary, we propose a novel 4D map representation, which can be used to build clean maps in dynamic environments. Based on it, we can achieve static surface reconstruction and accurate dynamic object segmentation. If you want to know more detail of our work, please check our paper and open source code. See you next time.